This lesson is on colligative properties, and the colligative properties are properties which depend on the number of solute particles in a given amount of solvent. In this case, a given mass of solvent, as we will be dealing with molality here and not molarity. Non-volatile is kind of a key characteristic of these particles. While non-volatile means they are not likely to form a gas. And so things that are volatile tend to vaporize. So gasoline, perfume, things with a strong odor tend to be volatile. Things that are non-volatile do not tend to form a gas. Things like rocks, concrete, wood are all non-volatile substances. Again, these are properties which change when a solution has a solute dissolved in it. In other words, the solvent properties become different when it becomes a solution. So the solution has different properties due to the colligative effect. And just to make sure you understand what I mean by colligative properties, if I ask you the question true or false, the above property depends to a large extent on the type of solute. That would be false. It depends on the number of solute particles only, not the type of solute particles that are present in the given solution. Three important colligative properties are boiling point elevations. So when you dissolve a non-volatile solute in a liquid, the boiling point of that liquid goes up, its freezing point goes down, also lowers the vapor pressure. So in terms of water, water freezes at 0 degrees Celsius, boils at 100. If we were to make a solution in water with a non-volatile solute, it would make the freezing point go down, the boiling point go up, or really extends the liquid range of water, making it freeze at a lower temperature, boil at a higher temperature. Again, test your understanding here. If I had a non-volatile solute, such as magnesium chloride, it would increase the vapor pressure of a solvent, such as water. That would be false. It would not increase. It would decrease the vapor pressure of that. And carbon dioxide as a solute would decrease the vapor pressure of water, would also be false. It would decrease if it was a non-volatile solute, but carbon dioxide is a volatile solute and therefore would not decrease the vapor pressure of water. It must be a non-volatile solute. So why do non-volatile solutes decrease vapor pressure? Imagine pure water here and a solution here. Here we've got 3 arrows indicating a higher vapor pressure. Here we've got 2 arrows indicating a lower vapor pressure. Note the top row of water molecules over here as opposed to over here. Here we have 7 water molecules across the top. Here we have only 4. So some of the non-volatile particles represented by the larger circles here, these cannot escape, and they occupy some of the surface positions that will block the water molecules from being able to escape. Plus, we must remember, if these are non-volatile solutes that are dissolved in water, they must be polar. And if they are polar, they're going to bond to the water molecules. And if they themselves cannot escape, that means the water is less likely to escape. So to summarize that, the solute particles are going to bond to the water molecules, holding them in solution. And then by occupying some of those surface positions, those solute particles are also going to block the water molecules from escaping. So 2 reasons you need to know why non-volatile solutes decrease the vapor pressure. Again, testing your understanding. True or false, a 1 molar solution of sodium fluoride would lower the vapor pressure of water to the same extent that a 1 molar solution of magnesium chloride would. This is false. Note these are both ionic compounds, and ionic compounds dissociate into solution. And in this case, they form a different number of particles present in the solution. Sodium fluoride will form 2 particles. Magnesium chloride will form 3 particles. Forming 3 particles is going to lower the vapor pressure, lower the freezing point, raise the boiling point more than just 2 particles. And true or false, elevation of the vapor pressure due to the increase in number of non-volatile solid particles will not affect the boiling point of a liquid. That is false. It will affect the boiling point of a liquid. Remember, a liquid will boil when the vapor pressure up equals the atmospheric pressure pushing down on that liquid. And if a non-volatile solute lowers the vapor pressure pushing up, you will need less pressure pushing down. And so to get the pressure up, you have to raise the temperature so it raises the boiling point. A couple of definitions. The boiling point elevation is the difference in temperature between the boiling point of a pure solvent and a solution. So water boils at 100 degrees Celsius, that's a pure solvent. If we make a solution that boils at 110 degrees Celsius, we would say that the boiling point elevation is 10 degrees. And freezing point depression is simply how much the freezing point of a pure solvent goes down when it is converted to a solution. So pure water freezes at 0 degrees Celsius, but a solution of a non-volatile solute might freeze at, say, -40 degrees Celsius. And so that would be the freezing point depression, 40 degrees Celsius. Why does salt cause ice to melt? In other words, why does it lower the freezing point? Think about what happens when water freezes. If all these represent water molecules, when it freezes, all the water molecules bond to each other to change it from the liquid state to the solid state. If we put a non-volatile solute in there, say glucose molecules or calcium ions or chloride ions, either something that is going to be a polar covalent compound or an ionic compound that is soluble, what happens is that gives water something else to bond to. And if water is bonding to the calcium ions or the glucose ions or the chloride ions, it is not bonding to itself. And if it is not bonding to itself, it is not freezing. So to put it in a simple form, solute particles interfere with crystal formation by giving water something to bond to other than itself. It does not bond to itself and therefore does not freeze. But again, if you get it cold enough, it will bond to itself and will eventually freeze. There is a limit to how much the non-volatile solute particles can interfere with the freezing of water. How to calculate changes in the boiling and freezing points of a solution. The change in the boiling point is equal to the molar boiling point constant times molality. And the change in the freezing temperature equals the molar freezing point constant change times molality. And so the molar boiling point constant and molar freezing point constants are just constants which relate molar concentration to change in temperature. Here's a sample problem with a molecular compound glucose. And so again, it's the change in the boiling. To calculate the change in the boiling temperature, it's the molar boiling point constant times molality. The molar boiling point constant for water is going to be 0.512 degrees Celsius per mole. Again, means for every 1 mole concentration, it changes by 0.512 degrees Celsius. And so we have to take the molar boiling point constant and multiply it by the molality. Molality is going to be the ratio of moles of solute per kilogram of solvent. So we have to take the 130 grams of glucose, convert that to moles by dividing by its molar mass. We have to take the 750 grams of water, change that to kilograms. And if we do all this math here, it's going to give us 0.493 degrees Celsius. If you want to see it solved to a smaller extent, this is the molality of the solution. And so again, it's the molar freezing boiling point constant times the molality gives you the change in the temperature. Note the problem asks, what will the boiling point be? We just solved for the change. And remember, it is boiling point elevation. So pure water boils at 100 degrees Celsius. If we add a non-volatile solute to that amount, then the final boiling point is going to be 100 degrees Celsius plus 0.493 degrees Celsius, or 100.493 degrees Celsius. So we have a boiling point elevation of 0.493 degrees Celsius. Freezing point sample, pretty much the same thing. We have the change in the freezing temperature equals the molar freezing point constant times molality. And so the mole freezing point constant for water is 1.86 degrees Celsius per mole. And again, we have to take the mass of the solute, convert that to moles, the mass of the solvent, convert that to kilograms. And here's the math for that. Here is converting mass of solute to moles, mass of solvent to kilograms. And we have a freezing point change of 0.091 degrees. And to solve for molality, if you want to do this in a stepwise fashion, you can calculate molality separate to get that. And we have a change of 0.091 degrees Celsius. And so your final answer then is going to be 0 degrees minus 0.091 degrees Celsius. Again, it's freezing point depression, makes the freezing point go down. Sample ionic problem. Here, we have to add one more factor. We have to multiply by the number of ions. Remember, for every 1 mole of an ionic compound that dissociates, you're going to get a multiple number of ions. In magnesium chloride, you're going to get 3 ions, 1 magnesium and 2 chlorides. And so we're going to have to multiply it by the number of 3. Again, molality is the ratio of moles of solute per kilogram of solvent. For 1 mole of this, we get 3 moles of ions. We have to multiply that by 3. Here's what the math looks like. We are doing freezing point depression, so we want to use the mole freezing point constant times the molality times the number of ions. And so it's the mole freezing point constant times molality times the number of ions gives me the freezing point depression. And then again, we just have to subtract that from 0 to get the final answer. To make sure you understand the idea of ionic compounds, what are the freezing points of 0.50 mole solutions of the following? Again, it's the change in the freezing temperature equals the mole freezing point constant times molality times the number of ions if it is ionic. And so the equation is the same for all of them up to this point. The number of ions will be different. And so for each of these, it's going to look like this. The change in the freezing point temperature is the mole freezing point constant times molality times number of ions. Aluminum nitrate has 4 ions, 1 aluminum, 3 nitrates. We'd have to multiply that by 4. This is a molecular compound, so this does not apply. I could either put a 1 there or just ignore it. This is a molecular compound, so again, that does not apply. This is an ionic compound made up of 1 magnesium ion, 1 sulfate ion, so there's 2 ions. I'd have to multiply by 2. Zinc chloride is made up of 3 ions, so I'd have to multiply by 3. Again, watch for ionic compounds. You have to multiply by the number of ions. What if I gave you this problem? Here we have not a solution described in terms of amount of solute, amount of solvent by a percent of the solute. So again, it's going to be the mole freezing point constant times the molality. And now if I have a 50% solution, I'm going to assume I've got 100 grams of that solution, and that's going to give me 50 grams of the solute and 50 grams of the solvent. So there's my 50 grams of solute that I have to convert to moles, and there's my 50 grams of solvent, and the problem really is the same. It's just that you have to assume that you've got 100 grams. Use the percent to figure out the amount of the solute and the amount of the solvent. Rest of the problem then looks exactly the same. 40.4 is going to be my freezing point depression. And my final answer then is it's going to make the freezing point go down by 40.4 or be a negative 40.4 degrees Celsius. And if you want an extra credit challenge, answer this question. Does ice melt faster in room temperature tap water or in room temperature salt water? Again, you want to take 2 equal-sized glasses, same temperature water, make one salt water, the other one tap water, put equal amounts of ice in both, and then see which one melts faster. Do not stir, shake, anything else. You just want to see, is it the tap water or is it the salt water that makes that change? For more details, see the website. Thank you for watching.